Alright, so Master Mason note, here today we'll be doing some stuff on this rock right here. Try to follow me along the best you can. We're not going to be bouncing around the room too much. We're going to be sticking this right here. Okay, we're going to hang it right here. This is the bar. Okay? It's like a regular piece of rock, don't it? Well, there's a lot of things going on it. But before we get too much into that, it's got a bad edge, it tilted in there, something happened. Let's take a look. Clearly, the bar, as you can see. English, working well. Anything under that situation is the. It is the. It's the reason you get paid. It is G equals the square root of M1, M2 over R1. Okay? This helps you. Sorry. Okay? R1. M1, M2, the bar. In this case, this is going to turn into an XY system. Now, obviously, we know that's a box, the bar. It's a three-dimensional object, no? There's your marshmallow. Here is your marshmallow. This one right now is obvious to you because +1 calculation somewhere's in here. Now, again, we're obviously using this. This would be the most appropriate NM number to define what X and Y are in this space-time. See, we're saying the limits of this are actually this one before it into the integral of that piece being finished. Not to say there's that piece, that's what that does. We're talking about the integral of the whole timeline. Now, Big Bang, always going to run through. People are like, yeah, great. That's the problem. You see special relativity is where it started. Special relativity. Then it generalized onto one of these, which in a process has an M1, M2, NM of having suborders, and therefore in its stack, general, here's the mass gap, here's how you work stacks, here's how you burn stone, there's product rules, there's air turbulence equations given the process, here's the piece of metal on the alien spacecraft. What happened over there is an electron or a neutron, proton crossing over a decay state that's proper for the solar fusion to reduce hydrogen to carbon, or iron, moving to iron, acting into its next step. Now that's the practical physical of that, and I'm going to crack you in the head. Alright, but obviously here we have the bar. Now again, let's talk about R. Let's talk about you. Because you are that rock. Alright? This is calculus. Here's that bar again. This one's a vertical straight line. You can go off any axis of this, make it a straight line here, make a triangulation of X, Y, and Z. Say that's that area, that's square of that area, the square of this area, the square of this area. Okay? And that's going to be determined by calculus. Alright, you'll see this most depicting first model. There, the state isn't really neutral. We're caught in that general relativity, special relativity notation. There's that rock. There's that process. There's that air crane with that thing over there and what's up in the standard model. +1. If I miss any of that calculation, going to correlate to the negative one side of this. I missed it. My timeline relative to this axis squared, you know, pi r, squared, you know, is going to give me this quadrant base. But here we're just using this variable to manage a timeline. And so I'm tracking those most of the times on the floor. This rock's 2 minutes. This rock's 4 minutes. See the average in there. That Celt type goes into the cuts, goes into the feeds and speeds by that, because that's an XY ratio that determines wear and serviceability. Those are both appropriate options. And you might find in the calculus of the brackets of what's going on in there that there are multiple types of rock and silica positions that actually determine what correct MG physics was. What was the mass gap? Those Italian rocks burn different because they need a higher water content in them, otherwise they're going to get roasted to burn. So, you know, clearly we can see here, but a lot of times you'll say, well, professor, what's that? Well, you could see how this would integrate into that tread line, yeah? Might have an effect on the flipping of the rock over here when there's the same change flip effect. Okay? So, in this way, we utilize this calculation like that. And it could be, you know, for my big one is a mason. I think a lot of the problems out here in this world today aren't necessarily any of these guys that do it. It's as much me. I don't, you know, have that proper communication. But let me first talk about what I see as a larger topic. You know, that mason game inside here. You see a lot of Illuminati. You see a lot of dudes wearing aprons. Then you see arguments. Okay? You know, I need somebody to come up with, you know, come vote for me and donate money on this cause so I can get Nancy Pelosi out. Huh. Like, that's been voted for. You need money to find a lawyer to get a case to say this illegal thing that they've done is done illegally. You can privately stand out there and say, I'm a better candidate, represent somebody, have a Mason brother stand up. He's like, he does that job every day. Every day. One of them, grab one of them, stick them in there. Why don't you ask some questions about physics? Maybe things would go a little differently when I got Nancy or whoever else, 1, 0, whatever defines mg to this rock, whatever the limit of the crowd or anybody else in this building, the resonant frequency off of these saws and the way I talk about things, have that effect. Because that's going to always lead to a better result. I can look at that. That is now mg physics. That is now this gravity that I'm going to put in here because those are those people names. Now, Rich's name's on there. That's usually why it's up there. You know, your girlfriend on here running that number, it's in there. That dog you bring into the table, when you start to look at this from other perspectives, and it's not just this one master I have to do, it's all this. This is my job. It's what makes me great. Catch you on the next one.